right, we're on the solutions video for AP Calculus, section 2.1b, page 145, 51 through 60, and then 63 through 66. About the alternate form of the derivative, here's the equation, lest we forget it. All right, number 45 says we're supposed to use the alternate form to find the derivative at x equals c. F of x is x squared minus 1. C is 2. So f prime at 2, we're going to take the limit as x approaches 2 of f of x, which is x squared minus 1, minus f of c. So you plug 2 into x squared minus 1. That would be 4 minus 1, which is 3, over x minus c. So x minus 2. Negative 1 minus 3 would be negative 4. So we have x squared minus 4 over x minus 2. Limit as x approaches 2. We're going to factor the top into x plus 2 times x minus 2. Then we can cross out the x minus 2 as long as x does not equal 2. And then we have the limit as x approaches 2 of x plus 2. We can now plug that 2 in for x and get a 4. All right, 51 through 60. Here are all the answers. I'm going to go ahead and put the book into view, and we can read the graphs here. So for 51, we've got a sharp turn at x equals negative 3, so it's not differentiable at negative 3. We got a sharp turn at negative 3 and positive 3 for 52, so that's the two places where it's not differentiable, negative 3 and positive 3. For 53, we have a vertical asymptote at x equals negative 1, so that's where it's not differentiable. 54, we have a vertical asymptote at x is equal to positive 1, so that's where it's not differentiable. 55, we've got a sharp turn at x equals 3, so the answer is x equals 3. 56, we've got a sharp turn at x equals 0, so we can't take a derivative. It's not differentiable at x equals 0. 57, you can take a derivative everywhere from x is equal to 1, greater than or equal to 1, and greater. All right, so you can take a derivative on that. There's not any places where you can't on this graph. 58, we got vertical asymptotes at negative 2 and 2. We've also got a horizontal asymptote, but that doesn't come into play. So negative 2 and 2, where it's not differentiable. 59, hopefully that's in your picture pretty good there. 59, we have a big jump discontinuity at x equals 0, so it's not differentiable at x equals 0. And then on 60, we've got a jump discontinuity at x equals 1. So it's not differentiable at x equals 1. Okay, so I wrote all the answers there. So if you need to copy any of those down, just pause the video. And I was able to fit 63 on there, and then I'll do 64 through 66 after I erase the board. Okay, so 63, we have a piecewise function there. We want to find the derivative from the left and the right. We're going to use the alternate form and see if it's differentiable at that point. So for 63, it's x equals 1. We've got x minus 1 all cubed, then x minus 1 all squared when x is greater than 1. So f prime of 1 to the left, that's when x is less than 1. We're going to use x minus 1 cubed. So that's f of x. F of c, we plug 1 into x minus 1 cubed, and that's going to be 0 over x minus c. c is just 1. So the 0 just goes away, and I have x minus 1 all cubed over x minus 1. One of those x minus 1s would cancel out, the one on the bottom, and you just have x minus 1 squared. Let me make sure you understand that. X minus 1 cubed over x minus 1. That one will cancel, and this goes down to x minus 1 squared. So just making sure you see what I did there. And so we can plug a 1 in. 1 minus 1 is 0, so that's 0. And then we'll do the same thing from the right. F of x is x minus 1 squared. F of c, plug in a 1, and you're going to get 0 over x minus 1. Then x minus 1 squared over x minus 1 would reduce to just x minus 1. We plug in a 1. We get 0. They are equal. So it is differentiable, yes, at x equals 1. And the slope of the tangent line at x equals 1 is 0. So that is the value of the derivative, which is just the slope. And yes, it is differentiable. All right, let's finish up by doing 64, 65, and 66. Okay, 64. We have f of x is equal to x when x is less than or equal to 1, and x squared when x is greater than 1. Okay, so f prime of 1 to the left, remember less than 1 would be 1 to the left, is going to be f of x, or the limit, as x approaches 1, of f of x, which is just x, minus f of c. All right, plug in 1, so c is 1, over x minus c. So x minus 1 over x minus 1, well, that's just the limit as x approaches 1 of 1, which is equal to 1. Now f prime of 1 to the right, this is left the limit, as x approaches 1 from the right. F of x is x squared. F of c would be plug 1 into x squared, and that's 1 squared, which is 1, over x minus 1. So I would have the limit as x approaches 1 from the right of x plus 1 times x minus 1, right? That's what that would factor into, over x minus 1. We can cancel the x minus 1 as long as x does not equal 1. So that's the limit as x approaches 1 from the right of x plus 1, and that's 2. So 2 and 1 are not equal. So the limit does not exist. So it is not differentiable. Where? At x equals 1. Now it's differentiable everywhere else, but it's not differentiable at x equals 1. So we can't get a slope of the tangent line there at x equals 1. That's because the two are not equal. All right, let's do 65. Okay, 65. We've got, this time we're going to use the same procedure. It's just this time c is 2 instead of 1. So I've got x squared plus 1 when x is less than or equal to 2. And then 4x minus 3 when x is greater than 2. Okay, so let's take using the alternate form, f prime of 2 to the left, all right, we're going to use this top one, is f of x, that's x squared minus 1, the limit, as x approaches 2 to the left, x squared minus 1, minus f of c. So plug 2 in, 2 squared is 4 plus 1 is 5, over let's see, did I skip 64? No, I didn't skip 64, I'm sorry. Over, let's see, x squared plus 1, sorry about that, f of x, x squared plus 1 minus 5, over x minus 2. So that's the limit as x approaches 2 from the left of x squared minus 4 over x minus 2. It should be the limit as x approaches 2 from the left of x plus 2 times x minus 2 over x minus 2. That's the limit as x approaches 2 from the left of x plus 2, and that is equal to 4. So if when we do it from the right, it's also equal to 4, then it is differentiable at x equals 2. So 2 from the right, and that's going to be the limit as x approaches 2 from the right of f of x, 4x minus 3, minus f of c, plug a 2 in, that's 8 minus 3, so minus 5, over x minus 2. So that's the limit as x approaches 2 from the right, 4x minus 8 over x minus 2. And hopefully you recognize you could factor out a 4. So factor out a 4 and you got x minus 2 over x minus 2. Kapow. As long as x is not equal 2. And that is going to be the limit as x approaches 2 from the right of 4. Limit of a constant is a constant, so that's 4. So these two are equal. So this function is differentiable at x equals 2. And the value is 4. We know the slope of the tangent line at x equals 2 is 4. All right, one more to go, and this one is the most tedious of them all. What's the last one? It often works that way, isn't it? The last problem is often the most tedious. 66. So we have f of x equal to 1/2 x plus 1 when x is less than 2, and root 2x when x is greater than or equal to 2. So we're going to go through the same procedure. F prime of 2 from the left, we're going to use the top equation, is equal to the limit as x approaches 2 from the left, f of x, 1/2 x plus 1, minus f of c. Plug a 2 in, that's 1 plus 1, so minus 2, right? Over x minus 2. So that equals the limit as x approaches 2 from the left of 1/2 x minus 1 over x minus 2. And so you might be thinking, I don't know what I could do with that. Well, this is a little bit of mathematical trickeration. You're used to factoring out whole numbers. How about we factor out a half? So that's the limit as x approaches 2 from the left. We factor out a half, what do we have? X minus 2. If you don't believe me, distribute that half. It'd be 1/2 x minus 1. So that's a good trick. You can factor out fractions too. Doink. As long as x does not equal 2. And that equals the limit as x approaches 2 from the left of 1/2. And that's just a constant, so it's 1/2. Okay, so 2 from the left. Let's do it from the right. F prime of 2 from the right is equal to the limit as x approaches 2 from the right. We're going to use the bottom equation, root 2x. So f of x minus f of c. So plug in a 2, that's the square root of 4, which is 2, over x minus 2. Well, what do you do when you have a radical? So we plug in a 2, we get 0 over 0 here. Well, we're going to try multiplying by a clever version of 1. So that's root 2x plus 2 over root 2x plus 2. And we're hoping in that process to eliminate that 0 over 0 situation we got here. Foil it out, and the middle term goes away, right? That was the whole point. So we've got root 2x times root 2x is just 2x. And then negative 2 times positive 2 would be minus 4. And on the bottom, we have x minus 2 times root 2x plus 2. Could factor out a 2. Out of the top, we factor out a 2. I've got x minus 2. And I hope you see where I'm going here. Because that allows me to eliminate that as long as x is not equal to. And I've got the limit as x approaches 2 from the right of 2. So I got rid of that 0 on the top over root 2x plus 2. Now we can plug in a 2. So that'd be root 4, which is 2. So that's 2 over 4, which is a half. So they are equal, aren't they? No. Equal. So it is indeed differentiable. It's a big word. At x equals 2. Because the limit's equal. There is no jump in the function there. Okay, no jump or break in the function. No asymptote there. No sharp turn there. It's differentiable. Okay, so at x equals 2. And the answer is, of course, what is the slope of the tangent line? Didn't really ask you for that, but it's 1/2. Okay, that does it for this video, and I will talk to you next lecture.